Okay, so now that we've looked at the basics of events, let's look at combining events in different ways and talk about the rules of probability there. So let's start with this. Two events are considered independent if the outcome of one does not affect the probability of another. Two independent events, A and B, have individual probabilities, probability of A, probability of B, that the probability of A and B occur together is probability of A and B equals probability of A times B. This principle can be extended to any number of independent events. Okay, so let me kind of underline this. That's the big formula that one needs to be aware of. Let me see if I can kind of clarify this up for just a second. When we use the word independence, we're not using Beyonce's definition that, all the women independent. No, we're not saying that it's this ability to assert one's authority and make our own decisions. We're saying that if you tell me something has happened and that gives me no information about another event happening, then I would say those two events are independent. Okay, so for example, if I am trying to track down a football player at the college, and I run down the hall and I grab the first student that I see, okay, and I'm trying to find a football player. So if I tell you that the first person I grabbed is a girl, do you know whether or not she's a football player? Okay, oddly enough, she's not, right? Most football players are boys. So the fact that I told you the gender, told you a girl, all of a sudden you're like, oh, wait, I now have information about whether or not there's a likelihood of this person playing football or not. Okay. Whereas if I tell you that I'm trying to track down a soccer player, and I tell you that I ran down the hall and I grabbed the first person I see, and I found a girl, a female student, and I started talking to her. Does that give you any information about whether or not I was successful in tracking down a soccer player for the college? And the answer is no. Okay, soccer's played by both genders, male and female, whereas football is only specifically played by men. So, knowing the gender gave me information for one sport, but didn't give me any information for another sport. So that combination of facts are what we consider to be an independent event or not. Okay. So another illustration, sort of in a mathematical way. What is the probability that rolling 3 6s in a row with a single die? Well, what's the likelihood of getting any 6 at all? Well, that's 1 out of 6. Now, if I got a 6 on the first roll and I roll again, does getting a 6 the first time give me any information about the second time? Nope. And the same thing with the third time. So each time I rolled the dice, I didn't know anything else about the next time or the previous times. So we would call each of those rolls independent events of each other. So it turns out if I'm playing a game of chance and I win by getting 3 6s in a row, the likelihood of that happening is 1 out of 216 attempts. So, not very likely. Okay, two events are considered dependent if the outcome of one affects the probability of the other. The probability that dependent events A and B occur together, probability of A times B is equal to probability of A times B. Given A and we're probability of B given A is probability of event B given the occurrence of event A. This principle can be extended to any number of dependent events. Okay, so it kind of goes back to what I was saying with independent events. Dependent events means if I tell you that a certain event has occurred, then you actually have more information about the likelihood of a secondary event happening. 3-person jury must be selected at random from a pool of 6 men and 6 women. What is the probability of an all-male jury? Okay, so probability of 3 men. Okay, so the first time I pick someone at random, there are 6 out of 12 individuals. So here's another characteristic of a dependent event. The next time I pick someone, I've already picked a guy, so there's fewer people in the room to pick from. So my probability of the next event depends on the probability of the first event. So there's now 5 guys to pick from out of a possible 11. And the third guy, well, that depends on who came before. So that there's now 4 guys in the room out of 10. Okay, so if I multiply all those together, 6 times 5 times 4, and 12 times 11 times 10, I should get 120 out of 1320, which is about 0.091. So less than 10% of the time would I expect to see something like that. Two events are called non-overlapping. If they cannot occur together. Another formal title is mutually exclusive. In case you've taken statistics before. Sorry, let me write that a little bit better. You'll hear mutually exclusive events or non-overlapping for our course. So something very basic like tossing a coin and rolling a die. I'm sorry, tossing a coin. Okay, either I'm going to have a head or I'm going to have a tail. I can't have both. So those would be non-overlapping events. Can't have them at the same time. For non-overlapping events A and B, the probability that either A or B occurs is shown below, which is this formula here. So the probability of A or B is adding the individual probabilities together. Okay, suppose we roll a single die. What's the probability of rolling a 2 or a 3? Okay, so 2 or a 3. So it's this or statement that we're looking at learning. Well, that's the same as the probability of 2 plus the probability of 3. And this assumes that they are non-overlapping events. If I roll a die, I can't get a 2 and a 3 at the same time. So I'm just going to add the individuals up. So 1 out of 6 times I'll get a 2. 1 out of 6 I'll get a 3. So that's, 2/6. When I add the fractions together, and that reduces down to 1/3. So 1 out of 3 times I would expect to get either a 2 or a 3. Alright, two events are considered overlapping if they can occur together. Is illustrated in the Venn diagram below. This is like picking a queen or a club. It is possible to get an outcome that is a queen and a club. And the formula for this, as far as how to find the or there, is we add the individual probabilities and then we subtract off the and probability, the likelihood of both happening. Okay, so let me kind of illustrate this with this card idea. Come down here. So what's the probability that in a standard shuffle deck we can draw a 5 or a spade? Well, let me write this out. Probability of 5 or spade. Well, probability of 5 plus probability of spade. Now, are there overlapping events? Could I have a card that has a spade and a 5? And the answer is yes. So I want to subtract off that. Okay, if it was a non-overlapping event, then I wouldn't have to subtract off the extra piece. So again, it comes back to overlapping versus non-overlapping determines which of the two formulas we're going to use. So the probability of a 5, in a deck of cards there are 52 cards total, and there are 4 5s. Out of the spades there are 52 cards total, and there's 13 spades. Now how many of of the 52 cards are fives and spades, that's minus 1. So little fraction rules here. 4 plus 13 minus 1. Denominator I don't touch. Numerators I just add them, subtract them like I see them. And so that gives me a total of 16 out of 52, which can reduce down to 4 out of 13. So 4 out of 13 times would I expect to see either a 5 or a spade.